You hear it all the time, right? That AI is learning. But what does that actually look like? Well, I'm here to tell you it's not magic. It's actually a series of brilliant logical steps. So today, we're going to pull back the curtain and show you the real building blocks of how a machine learns to think and even to see.
So let's just dive right in. What does it really mean for a machine to learn? And I'm not talking about science fiction robots. In reality, it's this powerful process of trial and error, all of it driven by data. It's about finding patterns and just getting a little bit better, over and over again. And it all starts with learning some pretty basic rules.
You know, the most common way machines learn, even today, is by studying examples where we already know the right answer. Just imagine giving a student a practice test, but you also give them the answer key. That's the core idea right there. It's a whole field called supervised learning.
The whole concept is actually pretty simple when you break it down. We feed the machine a ton of examples. The X here, that's your input data. Think of it as the features of a house, like its square footage or the number of bedrooms. The Y is the correct answer, the actual price the house sold for. The machine's entire job is to figure out the formula, the function that connects X to Y. So, how does it actually do that?
Well, it finds that formula using this really clever process called gradient descent. The analogy from our source material is just perfect. Imagine you're standing on a foggy mountain and you're trying to find the lowest point, the bottom of the valley. You can't see anything, so what do? You just feel the ground right at your feet and take a step in whatever direction is steepest downhill. Then you do it again and again. In this process, the loss is your altitude. It's a measure of how wrong your prediction is. And updating the weights, those are the little knobs the model can turn. That's just you taking that step downhill, slowly but surely finding the best possible answer.
So, at the end of the day, this whole learning process is basically used to solve two main kinds of problems. First, are you trying to predict a number, like a stock price or someone's age? That's called regression. It answers questions like how much or how many. Or are you trying to sort things into buckets, like figuring out if an email is spam or not spam, or if a picture has a cat or a dog? That's classification. It answers which kind. Two totally different goals, but they both start with that exact same process of learning from examples.
Okay, so a single model can get pretty smart. But let's be real, it could also have some serious blind spots. So what if, instead of relying on just one expert, we created a whole committee of them? This is where things get really, really powerful. It's an idea called ensemble methods.
This quote absolutely nails it. It's basically the data science version of two heads are better than one. Except here, we might be using hundreds of heads. By combining a bunch of simple, maybe even kind of weak models, we can build a single strong model that is way more reliable than any of its parts. Let's break down why this is such a game changer.
So to really get this, let's look at a simple model called a decision tree. It's just a flowchart of if-then questions. Super easy to understand, which is great, but that's also its biggest weakness. A single tree can get way too specific. It starts memorizing the noise and all the little weird quirks in the data it trained on. We call this overfitting. And what happens is it becomes an expert on the past, but the moment it sees something new, it just completely falls apart.
The brilliant solution to this is something called a random forest. Instead of building one fragile, over-specialized tree, we build hundreds of them. First, we give each tree a slightly different version of the data to look at. And then, and this is the magic trick, we only let each tree look at a random handful of the features. This is so important because it prevents any single tree from becoming an overconfident expert on one thing. It forces them to be diverse. Then, when it's time to make a prediction, we just let them all vote. All their individual mistakes tend to cancel each other out, and the collective wisdom of the crowd gives you an incredibly accurate and stable result.
Now, everything we've talked about so far requires a human to step in and tell the model what features to even pay attention to. But the next great leap in AI came from asking a really revolutionary question: what if the model could figure out the important features all by itself? This is the core idea behind deep learning. And this slide just illustrates that shift perfectly. We move away from what we call manual feature engineering, which is where a data scientist painstakingly handpicks what the model should look at, and we move into representation learning. This is where we just give the neural network the raw data and we say, you figure it out. It learns the most useful patterns and features completely automatically.
So how does this automatic learning actually work? Well, it all comes down to layers. A single artificial neuron, it's called a perceptron, is honestly pretty limited. As you can see on the left, it can only draw a straight line to separate data points. That means it fails at really simple puzzles that aren't, linearly separable. But when we stack these neurons into layers like you see on the right, something amazing happens.
The first layer learns simple patterns, the next layer combines those simple patterns into more complex ones, and so on and so on. Together, they can draw these incredibly complex, squiggly decision lines to solve almost any problem. And that stacking of layers, that's the deep in deep learning.
Okay, so stacking layers lets us learn complex patterns. That's cool, but what about a really specific type of data, like an image, where the arrangement of pixels is everything? You can't just scramble them up and expect it to work. For that, we needed a whole new kind of neural network.
See, if we just tried to use that multi-layer perceptron we were just talking about, we'd run into two fatal flaws. First, the number of connections between the neurons would just explode. A simple picture would need millions of parameters, making the model impossibly huge and slow to train. Second, to even feed it into that network, you'd have to flatten the image into one long line of pixels. And in doing that, you'd lose all the crucial information about which pixels are next to each other. You'd completely destroy the spatial structure you're trying to understand in the first place.
The solution is this brilliant architecture called a convolutional neural network, or CNN. It kind of mimics how our own visual cortex works. As you can see in this flow, the first layers learn to spot really basic stuff, like simple lines, edges, and curves. The next layer might combine those to recognize textures, like fur or metal. The layer after that might recognize parts, like an eye, or a whisker, or a car tire. And then finally, the top layer puts it all together and says, aha, that's a cat. It's this beautiful hierarchy of understanding, and it's all learned automatically straight from the pixels. So, we've figured out how to give machines sight. But what about language? Words aren't just a jumble of pixels. Their order is absolutely everything. I mean, dog bites man is a very different story from man bites dog. This is the unique challenge of what we call sequential data. This example from the source just perfectly captures the issue. If a model just averages the meaning of all the words in a sentence, words like not and good can basically cancel each other out, and it might think this is a positive review. To truly get it, a model needs memory. It needs to understand that the word not fundamentally changes the meaning of the word that comes right after it.
And that is precisely the problem that a recurrent neural network, or RNN, was designed to solve. The best way to think about it is like reading a book. As the RNN processes a sentence one word at a time, it keeps this thing called a hidden state. It's basically a constantly updating mental summary of everything that's happened so far. This memory, this summary, gets passed along from one word to the next, giving the network the context it needs to understand the meaning of the whole sentence.
So, everything we've just covered, these are the absolute core building blocks of modern AI. But you have to remember, this field moves at lightning speed. As this quote from our source material warns us, today's cutting-edge, state-of-the-art models are probably going to be tomorrow's history lessons. These foundational ideas are constantly being built on and sometimes even completely replaced.
And there you have it. We've walked through how machines learn from examples, how they combine weak ideas to become incredibly strong, how they build up understanding layer by layer, and how they process the flow of time and language. But this is just where we are right now. Which leaves us with one final, fascinating question to chew on. If this is how machines learn today, what on earth will they be capable of tomorrow?